Okay, so this work is a joint work with my advisor, Hector Geffner, and heuristic based on the lead relaxation represent the state of the art and are used by the best planners in the last international planning competition. However, in simple problems, these heuristics often fail, giving bad estimations and also bringing bad helpful actions. So let's see an example. Given this, the tower domain, where you start with all the blocks on the table and the scope is to build just a single tower, it turns out that all the pickups are helpful in the initial state, and also all the pickups result in the same cost estimate. But intuitively, the only good one is to pick up the block n-1, because we want to start the tower from the bottom and not from the top or the middle. So the relevance of all the pickups results from the chain pick a block, hold it, stack it on the goal position, but yet this chain can be proved impossible in all plans if it's understood as a sequence of causal links. So therefore, we think that these wrong pickups can be proved on structural grounds rather than heuristic grounds. So the goals of this work is to formulate and test a hierarchical planner that reasons with causal chains or paths and is built on top of three notions. First is path consistency that tries to capture the impossibility of a path. Then there is a decomposition scheme that decomposes the problem into subproblems. And then there is a new heuristic to rank the paths in a given state. An early version of this planner called C3 received the jury prize at the last planning competition. So for the rest of the talk, I'm going to give some background. I'm going to talk about path and consistency, decomposition, the path-based heuristic, and I'll end up showing an example of how actually the planner solves a simple instance, and with the empirical results. So the notion of paths and causal chains is built on top of the notion of causal links. And a causal link is a constraint that states three things. It says first that the atom P is a positive effect of the action A and a precondition of the action B. It also states that the action A precedes the action B. And really important is the third one, that it says that no action between A and B can occur if it adds or deletes the atom P that links both actions. So we will say that a sequence of actions and atoms form a causal chain where the atom is a positive effect of the previous action and a precondition of the next one. And if the last action of the causal chain is the end action, which is a dummy action that contains the goals of the problem as a precondition, we will call this causal chain a path. So the key idea here in this work is that some causal chains and paths are impossible in a given state S. So we try to capture this notion by inferring efficiently the sets of atoms that are true right before and right after each action of the chain happen from a given state. So this, we do it in a forward way, where the actions true before the first action is just the current state, and the set of atoms true right after the first action is just the ones that were true before, with the information, the precondition, the leads and effects of the action itself. So the key question is how to go from here to here, and we'll say that an atom Q that was true here will be also true before the next action if no action can delete it, meaning that all the action that deletes an atom from here either add or delete the link, so it's forbidden. And the same can be done backwards, where the atoms true right before the last action are just the precondition of this action, and we'll say that an atom that was true here will be true in this previous action if it was needed, if it was here, and there is no possibility of achieving it in this area. So we'll say that if there is no action that can add an atom that was true here, so it will be true also in this after this action. And we will do the regression operator, which is just include the precondition and delete the add effects. So we'll say that the fluents that are true before each action and are not the preconditions of the action itself we'll call them implicit preconditions of the action along the chain, and we will treat them as explicit preconditions. So when we combine the information forward and backward, we will get the labels that contains the set of atoms true right before and right after each action, and we will say that a chain is inconsistent in a given state if one of the labels of the chain include just a mutex pair. So this is a sound but incomplete definition, and can be computed in polynomial time. So moreover, we say that an inconsistent path, an inconsistent causal chain applicable in a state cannot be part of any plan from S. So let's see how we recognize an inconsistent path in the previous example. There is this path that tries to pick up the block 1, to hold it and stack it on top of the 2 in order to achieve the end action. And I want you to focus on the fluent on table 2. So on table 2 is true before peak and after peak, because it was in the initial state and pickup doesn't delete it. It is true also before stack and after stack, because it cannot be deleted if we preserve holding, and stack does not delete on table 2. And will be true also before the end and after the end, because if we maintain the block 1 on top of 2, we cannot delete the block 2. And we will find that in the last level, we have this mutex pair on table 2 and onto 3. Therefore, we'll say that this action doesn't have to be considered if the only justification is this inconsistent path. So the path algorithm in C3 regards just the consistent path in a state as a plan skeleton to be executed in that order once the other preconditions of each action are achieved. So basically, the plan algorithm reduces the first action of the path if it is applicable in the current state and update the states of the search, and otherwise it will extend the current path if the first action have an open precondition, meaning that the precondition is not achieved. So the initial path is just the end action, and the initial state is the initial state of the problem. And it will happen a backtrack only if no extension is possible. And that means if there is no possible consistent path in a given state. So let's see informally an example of how the algorithm solves. So let's say that Q is in S in the initial state and P not, and both atoms are in the goal. So we will start with the end action, and the first thing that we have to do is to extend the open precondition P. So we will find a path that has to be consistent, and the first action is applicable. We'll apply the first action, and then let's say that there is another precondition in A2 that is not achieved in the state, and therefore A2 is not applicable. What the algorithm will do is do another extension until A2. So it will find a new path to extend the old one, and now it applies the first action that is applicable, and imagine now that all the preconditions have been achieved of A5, so we will reduce A5. If all the preconditions of A2 are achieved, we will reduce A2. The same with A3, and if we are able to reduce the end action, will mean that we have achieved the goal. So, more formally, if there is a path and it has an open precondition in the first action, meaning that it's not in the current state, we need a new path that supports this atom and where the first action is applicable in the state. Therefore, we will result with a reducible path composed by the new one and the old one. So the key issue here is how to compute and order the possible extensions. So we have two ideas. The first one is that we only will compute what we call the minimal path. And minimal paths just say that the path that we consider are the paths that have that all the actions support the atoms with a minimum H max, meaning that are the best supporters. And about how ordering the possible path, how to know which is the best path to support the old one, we'll make a new heuristic that consider a path and a state. So the idea of this heuristic is that it will estimate the cost of achieving the goal along the path from a given state, and it is built from a known Bayes heuristic. So the idea is that if we need to estimate the cost along a chain, we'll need to approximate the state true right after each action of the path is applied. So from a path, and we'll see in the next slide how we use this sequence. So from a path, we generate a state sequence where the first action, that is here, is just the current state. And the next one is the current state, well, this state, updated with the effects of the set of actions in the relaxed plan for achieving the preconditions of the next action from the previous projected state. And also, we take into account the effects of the action itself. So this propagation will be done until the end, and we'll get a sequence of projected states. So given this sequence and a path, we'll say that the path heuristic is the summatory of the cost of achieving each precondition from the projected state. And where this estimator is just any base known heuristic, can be the additive one, the max, and is computed excluding from the computation the actions that interfere with the causal link of the action. So the good thing here is that the path heuristic takes the leads into account even if the base one doesn't. So let's see an example of how the planner works. This is the Sussman anomaly, where the subgoals cannot be tackled just forgetting the other goals. And we'll see that the notion of implicit precondition helps to interleave the goals. So the first path that the planner finds is actually inconsistent. And we'll see why. Let's see the atom on table A. So if we pick B and maintain the atom holding B, on table A cannot be deleted. So it will be true after stack BC. And if we maintain the atom stack BC, we won't be able neither to delete the atom on table A. So it will be maintained until the end, and then have this other precondition. And we'll find that the last level has the multi precondition that is on table A and on AB. So the planner will continue looking for paths, and the next one that it finds, it's actually a consistent path. And we'll see that the atom on table A persists in this first causal link, because we maintain clear A, so we cannot move on table A. But it does not persist because P cap A delete actually on table A. So we won't have any inconsistent in the mutex level until the end. But the interesting thing here is what happened with the atom on BC that is a precondition of the end. So on BC cannot be added if we maintain this atom on AB, basically because we cannot move. So we'll say that on BC in the backward propagation will be true right before the stack AB, and if we maintain holding A, we won't be able to put on BC because the arm is locked too. So it will be true also before PK, and if we maintain just clear A, it won't be true here. So we'll say that on BC is an implicit precondition of P cap A. So now the algorithm will apply the first action that is applicable, and it will try to apply the next one. But as this precondition is not achieved yet, what it will do is it will extend this chain with a new one. And the chain that it founds is actually the plan itself. So it starts with stack CA, then it executes put C, it picks B, it stacks BC, it picks A and stacks AB, and can reduce the end. So with just two paths, we are able to solve the Sussman anomaly. So what happened in bigger problems? So we get empirical results comparing with FF and Llama, and the planner is evaluated using a timeout of 2 hours and a memory out of 2 gigabytes. So from a pool of domains from the last planning competitions, we have in total 785 instances, and C3 solved 684, one more than FF, and much less than Llama, 728. But the most important is that 612 of them are solved backtrack free. And by backtrack free, we mean that it chooses a path, and it follows it, and it doesn't get confused. It just goes straight to the goal. So about plan quality, C3 finds plans 14% longer than FF, and Llama finds plans 6% longer than FF. And C3 is 3 times slower than FFs and 6 times slower than llama. Here, llama was executed just with, not in any time, was reporting just the first solution that it found. So, as to summarize, we think that reasoning along causal chains and paths appears to be important in planning. And so far, we have focused on the study just of paths, and we have developed 3 techniques: path consistency, a hierarchical planning scheme, and a path-based heuristic. The resulting planner performed pretty well, solving 78% of the problems backtrack-free. And as a future work, we want to consider SAT-like learning in the context of path-based planning. We want to use the path-based heuristic in a forward state planner, and we want to try to characterize the line that separates easy from hard problems. And by hard, I mean puzzle-like. And that's all. Thanks.
We have plenty of time for questions, so head at it.
So, in cases where the problems are solved back-free, is the kind of doing that still
Let's say that it's competitive. I mean, it works fast. If it gets lost, it's much slower. But still, yes. We compare it first with the ones with the enforced hill climbing, like using, as it's an incomplete algorithm. So we try to use enforced hill climbing to compare, because it's also an incomplete planner. And if you compare, these times are really close. I mean, but then if it gets lost, it's like a complete algorithm. It's much harder. With the results, well, in the paper there is actually the whole table with more details of all the performance.
So by easy and hard, you mean backtrack-free, not backtrack-free?
That's one of the ideas. Yes.
Could you go back to the list of domain fields, right? I mean, probably you know this domain with a backtrack-free only.
Yeah. For example, blocks were all backtrack-free. The one that is really hard is free cell. Free cell is really hard to solve. Which else? Pipesword also. But domains like satellite, gripper, logistic blocks, all of them were solved backtrack-free. Sorry? Yeah, thank you. No, the plans in logistics, in blocks are just like, I think, if I remember well, like 8% longer, more or less, than FF, yeah. And the key issue is the heuristic that we use to choose the path, because it actually finds the best path to decompose the planner. So if we choose any, maybe the plan can be longer. Yes. Mm-hmm. Yeah, that's the idea. And also, it fails sometimes because we have the problem as we consider only the minimal path, we are like stuck with the helpful actions in a way. So one thing that we want to do with the learning is to get away from this minimal action, from these helpful actions. Okay, so if after you can give me a pointer, That will be great.
Anything before 95.
Okay.
Because of the change, that's true that, of course, the notion is well established and has a long history and so on, but usually the mechanisms for doing inference of Gaussian change almost non-existent. So the idea to reason about Gaussian change, you can do inference. And
No,
there
I
are
think there's one on partial groups, for example, in partial language. So it exists.
Okay, my turn. Minor comment. I'm not sure path consistency is a good name for this because it has a very technical meaning in the CSP literature, and so it might be a good idea to name it something else. My other question is in the blocks example, you're basically finding out that the different portions of the goal have to be ordered in a particular way. And I'm wondering what relationship, if any, that has to the ordering that can be determined by the ordered landmarks work, for example. Do you have any thoughts on that?
I should think about this, but no, I don't know if Hector you can.
there's a relation about it's very in order, but now the proposition and the causal change do not have to be landmarks. So in this case, it's very in order, so much as not necessarily landmarks, but history can be also from the same customer.
Actually, in this particular case, landmarks will not help because what was on the top there, block 1 or block N? And the goal.
The goal was block 1.
1. So block 2 being on block 3 is not a it's not any relevant for being for block 1 to be on block 2. So if you look what is needed for block 1 to be on block 2, the fact that block 2 is on block 3 is not there. And it's not required. But because the blocks are tricky, that's it.
Yeah.
So I wish for landmarks.
That's a good point, I think. You're saying that from the point of view of landmark, they're not ordered.
Yeah.
Some goals from the point of view of landmark, they're not ordered. They are ordered because both have to be true at the time of the goal. That's a good point. So the ordering here will be different from landmark. So here, the two propositions have to be true at the same time, and the only way to get them both at the same time is to achieve one first and the other second. You cannot go the other way around.
What you can do is just rule out chains that don't respect the landmark order.
Yes. So the question is whether inference ever do it automatically.
Yeah, another idea is to consider